En esta cuarta sesión se tratará el tema de TIC para fomento de la economía popular y solidaria. La creación de una economía social del conocimiento ha llegado a ser uno de los pilares fundamentales del Plan Nacional del Buen Vivir en Ecuador. Se ha hecho especial referencia a la importancia de un nuevo enfoque, el acercamiento del procomún a la creación e intercambio de conocimientos y con ello al desafío de aplicar TIC para empoderar y expandir el rol de la economía popular y solidaria en la transformación radical de ideas y prácticas asociadas con modelos progresistas de desarrollo económico y social. Los expositores de esta sesión explorarán la relación entre las TIC y la promoción del cooperativismo, los valores y prácticas del procomún y analizarán cómo los sistemas de tecnología abierta y sistemas de conocimiento abierto están relacionados al nuevo rol económico, social y político que la economía popular y solidaria está llamada a desempeñar. Y vamos a comenzar entonces con la primera exposición de la tarde. Es una videoconferencia con Joshua Pearce. Joshua es ingeniero académico en Michigan Tech. Recibió su PhD en la Universidad Estatal de Pensilvania, donde su trabajo en protocristalín ayudó a desarrollar a bajo costo la tecnología amorfo solar de silicio. Desarrolló los primeros trabajos sobre tecnología apropiada de código abierto, que es la tecnología que diseña aspectos medioambientales, éticos, culturales, sociales, políticos y económicos de la comunidad que están delineados de la misma manera que el software de código libre y abierto. Joshua Pearce nos acompaña con el tema Rebaja de costos con material científico de código libre y abierto. No sé si ya lo tenemos a Joshua.
Thank you.
Joshua, welcome.
Okay, thank you. And so let me begin. So what I would like to talk to you today about is how to radically reduce the cost of scientific equipment using a free and open source approach. And so first we're going to go through the basics of open source hardware, open source electronics, and open source 3D printing. Then we'll discuss the open source lab and how free and open source hardware actually works, using examples from existing scientific enterprises, an optics library, prototyping, applications in electronics, chemistry, biology, and environmental science. And then finally, we'll look at advanced applications, how citizens can become scientists, and how we can push the policy to make this happen in the future. Even for those of you that aren't scientists, the reason that this is so important is that free and open source software and hardware can radically increase the speed of development of science, which increases the speed of technology, which is better for the environment, or better for the economy. So open source hardware is relatively, probably already familiar with source software. You might use Wikipedia to look up things. You probably use Linux, which is an open source operating system every day, even if it's a computer. If it's Google or Facebook or from any of the major, all have open source software running on the back end. And the reason that these companies do this, first of all, it's usually free, like this operating system is free. But the primary reason they use it is because it's superior. It's superior because you get many different all over the world collaborating to make it a great and useful product. Just because it's free also doesn't mean that it's anti-business. For example, Red Hat makes $1 billion a year providing support for free and open source software. Now, open source hardware is developed in the same way as open source software, except rather than providing the source code for a program, you provide the source code for the hardware. So this is an example of an Arduino open source microcontroller. They cost between $20 and $50. They're kind of cute little hand-sized things, and if any of you have done automation work, know that in the past it was very difficult. But for these things, I can teach a student how to automate an experiment in about 30 minutes, and the total cost was around $20. The code, the schematics, and the designs are all freely published and available online. It has an enormous community all over the world of people helping and assisting and making this microcontroller do new and interesting things. So as an example, you can make an Arduino-based oscilloscope. Oscilloscopes normally cost between hundreds of thousands of dollars, And you can have an entry-level one where all you basically need is the computer you already have and the microcontroller. Similarly, for biologists, you can make an Arduino pH meter for chemists. Again, this costs far less than a typical commercialized closed-source proprietary pH meter. Now, there's hundreds and hundreds of automation projects that have been developed using the open source Arduino. But of all of them, the one that's the most interesting, at least for me, is open source 3D printing, or the RepRap. So RepRap stands for Self-Replicating Rapid Prototyper. It is a 3D printer. It extrudes plastic filament by heating it up, going over a surface in 2 dimensions, just like a normal printer. And by doing this, it can build up 3-dimensional objects. It can also build the components that make itself up. So the picture on the left is the first generation RepRap, and on the right is 2 of my students demonstrating its use with the One Laptop per Child computer developed by MIT. Because the RepRap, these open source 3D printers, are open source, people from all over the world, including this is Brennan, one of my students here, is improving it. They're building on the design, they're making it better. And so this kind of version 2 of the RepRap uses less parts, it's easier to put together, and costs less money. Then here's version 3, and this gets to how you can start to use this open source approach to make very valuable scientific equipment. In this picture, you see an OpenSCAD model for an automated filter wheel. An automated filter wheel simply turns and puts a filter in the path of a light, and I use it for my solar photovoltaic research to be able to test how solar cells do with different colors of light. These filter systems are very expensive. The commercial ones are over $2,500, and the one that I had broken, I needed a new one. But rather than go to the back of the store and buy one, it was pretty expensive, we designed one using OpenSCAD, which is an open source CAD package that's freely available for everybody. The computer that it's running on is an old computer that was thrown out, but we revitalized it with a version of Linux, which is much faster. It's a much better operating system than, say, a Windows type machine. And then we used the 3D printer to print out our filter wheel. And so we were able to have an automated filter wheel that was exactly what I wanted for our lab, superior to anything on the market, for $50 instead of $2,500. And we continue to do better. So now we've pushed the price of the RepRaps down to under $600. This particular version can be built in under 24 hours. If you have 2 people, it can be done in 5. And we've continued, this is our latest design. It's a Delta RepRap printer. And everything that the others could do, it has less components, it costs less money, and now you can build it's as good as the ones on the market that used to cost $20,000 for under $500 and build it. Then use this printer to develop very high-end scientific equipment. And when you do that, you can make an open source lab. And so I want to go through some examples of how scientists can use this open source philosophy to drive down their research costs. And so imagine if you have a scientist, like the one in the upper left-hand corner here, and she designs a test tube, and she shares it with the internet community. Then 2 other scientists that may not even know her, and they would probably work in a different country, don't necessarily even speak her language, can download her design, and then they build 2 other things. And so they build a test tube rack and a spinner in order to be able to do like a centrifuge. So then, because she shared her innovation with the world, she's repaid by the people that come after her developing her technology even better. And so now she can download both the test tube rack and the centrifuge and print them for a fraction of what it would cost her to buy them on the open market. And so it's in everyone's best interest to share as much as they can, because the more people that build on their design, the better it will be for the scientists down the road. So let me give you an example of this. This is a chopper wheel. And because the way that we catted it, we made it parametric, you can change the number of slits that it has. Now, this is something that would normally cost like $25, so it's not an overly expensive item, but it's something where you don't, for instance, know exactly how many holes you want until you've actually started to do the experiment, so you usually have to buy several of them. But with this technology, you can change one number in the script and then print out a new one. So this would cost $25, say, for Third Labs, but we can print it sense. So here's a bunch of different examples of optics equipment: lens holders, filter holders, optical rails. Optical rails sell on the market for $380 a meter. You can build one using this kind of mechanism for under $12 a meter. Lab jacks, magnetic bases, and even advanced physics equipment like a Michelson interferometer. And so we built an entire optics library and showed that you could cut the cost of doing science by at least 97% and usually 99% or more. And it goes for other applications. Oftentimes, one of the most expensive things that a scientist does is prototyping. And so we were working on a polymer-based heat exchanger, and nobody even in the US could do it. We had to send away to Germany to have them do the prototyping for us, the laser welding. And this got very expensive. They were charging us $300 per item. And we wanted to test a bunch of them, and it was becoming prohibitively expensive. So what we did is we found an open source design for a laser cutter. We adapted it for our own needs. And if you look in the upper right-hand corner, all of the black components we designed and printed to meet our application exactly. And so we were able to create a polymer heat exchanger prototyping system, a laser welding system, for less than it would have cost us to do like 3 or 4 experiments overseas, and now we can make hundreds of them. And so this one device has saved my labs tens of thousands of dollars already. For those of you in chemistry and biology, centrifuges, there's a whole slew of a different array. The one on the left-hand side is the Dremel fuge. You attach a Dremel drill, just an ordinary drill, to this chuck that you can print out for, again, a few pennies. And now you have an ultracentrifuge that normally runs thousands of dollars. And so I hope you're getting a feel for how you can get the same quality of the technology and you can share it digitally so that everybody can get using the exact same device, and it completely obliterates the normal cost of there's pipette racks and an auto pipetter. Again, it's a tool that is in almost every biology or biochemical lab, and you can print it yourself, again, for pennies on the dollar. It can make advanced equipment. This is the open PCR for doing DNA replication. Again, less than 10% of the cost of a normal proprietary one. This is an open source colorimeter that we developed in my lab. It was based off of an Arduino Uno, so this total device cost under $25. Has a printed case, and as you can see in the lower right-hand corner, it is as good as a commercial one that costs over $2,000. Magnetic racks. A single magnetic rack for doing pulling out chemicals within a test costs more than the 3D printer that you can use to make it. So not only can you make normal test tube racks and simple things, but you can start to make more advanced equipment, such as this. This Public Labs is a nonprofit group in the US that made a spectrometer that you can literally take anyone's cell phone and turn it into a useful scientific instrument. And so for doing lab work in the field, for forestry rangers, for biologists and ecologists, it's an invaluable tool, and it's leveraging equipment that everybody already owns, a smartphone. This technology is, again, evolving as people from all over the world are contributing their ideas to make it better and be able to be competitive with the high-end scientific equipment that would, again, normally cost thousands of dollars. Sensorica is a group that started in Canada that, again, is doing a lot of this open source developmental work. The Mosquito, this is their design for an open source force displacement sensor. And this is starting to go up the kind of ladder of technological sophistication. We're getting better and better. And again, these aren't 3D printed, and I guarantee you, if they don't figure out how to make them 3D printable, my group will. A group in the University of British Columbia, developed a digital microscope design, again, where you use your cell phone as the camera, and the entire thing is printable. The lenses, they were able to pull out of the discardable cameras that tourists use. And so you go to your local Walgreens or your local tourist place, pick up the used cameras, take out the lenses, and then you can make microscopes that are good enough to do kind of preliminary scientific research. They're certainly good enough to teach students. And so as an educational resource to provide extremely inexpensive microscopes, this is a great tool. Or you can go on the high end. On the right-hand side, the University of Cambridge's Open Lab Tools initiative has made a $8,000 optical microscope. It does, self-zooming and all that. It would normally cost $80,000. Again, all of the plans are open source. Download them and immediately begin to use it. They're kind of taking the next step in microscopy. This GNOME system, it's an open source multi-channel imaging vector data acquisition and visualization system, allows you to do SPM techniques like scanning tunneling microscopy or atomic force microscopy. And so this is moving to the nanoscale. This is top of the line, high-end scientific equipment that is free and available for everybody. The software is. And as we reduce the cost of scientific equipment, not only does it help our best kind of top labs, our top national labs, our top university labs, but it also makes it possible for citizens to start to think about being scientists. I really like this design, and this was partly kind of influenced by the tragedy in Japan, where the Japanese public was not able to trust their own government or the authorities in the industry to know what the radiation was coming from Fukushima. So this is an open source Geiger counter that anybody can print and put together the electronics and begin to use. And so people all throughout Japan and all through the rest of the world too have been using them, have been taking measurements and then uploading them. This is an image of a map of Japan during the disaster, where citizens were uploading their data to provide reliable information for the rest of the public. And so we can start to become more participatory in science, and this data all is very good and useful, and real scientists, the kind of professional scientists, can use it as well. Now this is the future. As we get better and more sophisticated scientific equipment, we will begin to be able to put many functionalities together. For those of you familiar with Star Trek, the fictional television show, they had a tricorder, which was a handheld device that could do basically everything a scientist could ever want. And a university professor now in the US is developing a real tricorder. And so this particular device has like 25 sensors in it. It's all open source. It runs off of Debian Linux. It has a printable case. Everything about it makes it possible for the next generation to begin using it. And so particularly for people that do field work, a device like this is going to become indispensable. And it costs, again, pennies on the dollar for what it would cost for a proprietary commercial device. Now, all the digital fabrication that I've been talking about is based purely on the low-end RepRaps, these sub-$500 3D printers that only print in plastic. And that's sort of where the technology is right now. But we're quickly moving past that. And instead of just being able to print in plastic, we can now start to print in conductive polymers. We're also putting together a mill so that we can mill our own electronics boards. And so even the most expensive component to some of the scientific equipment I showed you was the Arduino or the electronics. But when you can make it yourself for basically the cost of the board, it really pushes the cost down. Building an actual stepper motor so that the 3D printer is completely self-replicatable is within our reach. We will have that soon. And then we can start to do things like think about making a smartphone. Maybe we have to still buy the chips, but we can do all the electronics and we can print the case. And then next, we can start to print the chips. And eventually, we can move into all materials. So what about big, large things? What about large scientific tools that need to be made out of metal or chemical reaction? Or can we do that? The answer to that is absolutely yes. This is the first metal printing RepRap that I'm aware of, and we developed it at Mission Tech, where we attached a welding unit, a MIG welder, to an upside-down delta bot. So I showed you the kind of delta RepRap before. This is just an upside-down one. And so we ground the plate sitting on top of an insulator and run we hold the welder unit still and we run the platform underneath it. And so you can build up three-dimensional objects out of steel. So we've made a couple simple things to demonstrate that it works, and we're beginning to work on the development of it. And so very soon, the scientists, the technologists, will be able to literally choose from any material system and begin to print it. And this allows everyone to scale their ideas. Once you've designed something, you can share it with the rest of the world, and then everybody can have that thing for exceptionally low costs. So as an example, this is one of the first sprockets that we printed that we can use in a device we call the RecycleBot. This RecycleBot device uses a windshield wiper motor and a simple block heater to take milk jugs that we shred in an office shredder, we push it through the recycle bot, and then you can see the filament coming out on the right-hand side. And so we're able to make the raw feedstock for our 3D printers from waste plastic. Now, all the numbers that I've been quoting you on costs have been US dollars based on commercial filament. Commercial 3D printing filament costs between $35 US and $50 US. You can take 20 milk jugs and make a kilogram of useful 3D printable plastic for 10 cents of electricity. And this is all just coming now. So we are going to be able to push the costs for the most sophisticated scientific equipment down into the basement where everybody can get a hold of it. Now, there's a lot of work happening on this sort of front right now. There's many groups. Basically, every nation has already been doing some open source scientific, but we can go much further. And to go much further, what we have to do is think about systematically making all the tools for scientists extremely inexpensive. And so there's 5 policies that can implement that is possible. First, you form a task force with your best scientists, the top of the cream of the crop, the ones that know what equipment is needed and are able to think about strategic national goals. So what scientific problems is Ecuador trying to tackle? And what equipment do you currently bring in from somewhere else in the world so that you're sending money away from your country rather than keeping it inside? Then you look for high ROIs. ROI is return on investment. And so if you can pay a scientist $20,000 to develop a tool that then makes it possible to save $2 million in scientific funding for other people to build that tool, that's your win. And so you tackle the free and open source scientific tools that have not already been designed. The second thing is, after you figure out, say maybe like the top 100 designs that need to be done that haven't been tackled yet, you use federal funding, scientific funding that would normally go to just purchasing equipment. Instead, use that funding to design the equipment. And then the person that won the grant not only gets the piece of equipment that he or she built for themselves, but they can then provide it on the web, and then everybody throughout the world, scientists that are able to. Third, you should collect all of this equipment together in like an online catalog of validated scientific tools. So when our lab designs a new tool, we validate it against one of the commercial products to make sure that it's actually performing up to spec. This needs to be done for every scientific tool that's put. So you could have sort of a green-lighted, like a blue star listed high-quality scientific equipment, and so the scientist would know and be able to trust that what they're downloading from, say, this government open-source hardware site will work and be valid. Fourth, a way to spur this and also to create kind of entrepreneurship within the country is to provide purchasing policy preferences for FOSH for all government-funded projects. And so if a government is going to put money into buying scientific hardware, that scientific hardware better be open source so that they know they're getting the best possible deal. And if this is known, then companies will be incentivized to provide the source code for their equipment that they're already selling, and also to develop and make better the open source hardware designs that already exist. And then last, but not least, you want to be able to make this equipment at the location that needs it. So what that means is having a maker space, a basic place where, say, an entire public university could go that would have a machine shop, some of the basic 3D printers and laser cutters in order to be able to make this equipment, a basic electronic shop. For the universities that don't have that, making a small investment in these maker spaces will allow the university to make tens of hundreds of thousands of dollars of scientific hardware for much less than they could have bought it for. And so if you have a limited amount of money, you're able to stretch that money as far as you possibly can. And so everything that I've talked about, we source repository on Apopedia. We have all of our methods, the designs, the code, schematics for our hardware, build instructions, literature reviews, and then free access to every academic article. So I thank everybody for their time and attention, and I'd be happy to take any questions.
Tal vez tienen alguna pregunta para nuestro expositor. sobre el tema? ¿Hay alguna inquietud? Por favor, si nos ayuden con el micrófono, por favor. Tenemos una inquietud.
We have a question, Joshua. Please stand by.
Mi consulta refiere a que al hecho de que el
My
sector de la
question has to do
economía
with
popular y
the fact
solidaria
that the
no tiene mucho poder
people
económico,
don't have a
¿cómo
lot of
puede
economic
acercarse
power.
a
How
la
can
tecnología de las
it
impresoras 3D,
go
por ejemplo?
to
¿Qué
be able
proyectos
to
hay entre
use
naciones?
3D
No sé.
printing? Are there any type of agreements among nations that you know of?
I don't know of any agreements between nations, but anyone with access to roughly $500 in funds, and so most scientific labs would have access to that in all of the countries, would be able to afford the first print, and then they can use that printer to print more printers and provide them to a larger swath of the population. That's why these maker spaces are so valuable, because for our there's still 3D printers, but we don't use them all the time. And so if it's made available to the public then in a makerspace, then everyone would have access to it. And the costs to operate it are really just the electricity and the plastic, which are fairly trivial, particularly when you use recycled plastic.
Tenemos otra inquietud.
Sí,
We have another question, Joshua.
la pregunta va referente a cómo
The question is
manejar el
how to
tema de
handle
propiedad
the issue
intelectual
of
con el
intellectual property
acceso a las nuevas tecnologías.
with the access to
Ahí
new
incluimos
technologies.
toda la diversidad que tenemos al momento,
We
como es
can
biotecnología,
certainly talk about biotechnology,
biología estética.
biology, aesthetic
Y en este
biology.
sentido
And in
quiero
this regard,
hacer referencia
I would like to refer
cómo establecer para todos los
on how
sectores,
to
tanto de
establish
las
for the
TICs
sectors
como también de sectores como la biotecnología,
and
un
sectors such as
enlace,
biotechnology, and
una
to see how we
conexión
can
tanto con el
have
sector
a
público, sector
liaison between
privado
the
y
private and
sociedad
public
civil
sector and
en la
civil
aplicación
society
de
in
ATMs,
the
que son
application
acuerdos
of
de
ATMs,
transferencia
which
de
are
materiales.
material transfer agreements. Can you shed some light on that, Joshua,
So-
please?
Yeah, so intellectual property, as it's sort of been practiced for the last several decades, is changing rapidly, and I think part of why this change is necessary is because of the potential, because of the rise of open source technology and its dominance technically, but now also this digital fabrication, this ability to make everything from hard plastic objects to chemicals, say in open source 3D printed reaction. So I foresee something similar to what's happening in the software world, where in the beginning software was all open source, and then it got closed down for quite a while, but then slowly it started to rise up, become superior, and now it's sort of like that is similarly going to happen with all the other types of technologies. All that means is that the business models have to change. So rather than sort of operate like a Microsoft, where you sell people software and you make your money that way, you need to operate more like a Red Hat, where you give the software away for free, but then you charge people for the services. And sort of similar, if you, like say, take the example of a biotech firm, they might have open source hardware that develops it. They might have open source chemicals and strands of ways that they're making their biotech, but then they offer either services or because they're sort of a first mover and they can make the chemical or the biochemical faster and better than everybody else, they still sell it. But they don't have the ability to have a 20-year monopoly to hold back, to like literally hold back science and technology for 20 years while they make monopoly profits. So I think monopoly profits are going to go away, but the ability to make quite a bit of money and have a successful business is still certainly there.
¿Tenemos otra inquietud?
We're waiting to see if we have any other questions, Joshua, please.
Bueno, entonces agradecemos a
Apparently
Joshua
not, so
Pearce,
we'd like to thank you,
académico de
Joshua.
Michigan Tech, que nos acompañó con el tema rebaja de costos con material científico de código libre y abierto.